Um, Good morning, all of you. So, for today's class, last class I have discussed about the optical fiber numerical aperture and acceptance angle and the critical angle types of the ray. Okay, so today I'll start with the types of the ray and what are the modes are available in the optical fiber. Okay, so when the optical signal is incident on the optical fiber, uh, it can it can propagate through the different orientation of the light. So what is the meridional ray? Meridional ray. Another is the skew ray. Depending on the types of the fiber, what are the materials are there inside the fiber. Based on those things, the light can the orientation of the light and the direction of the light it can also change. If forget about the fiber, if you think any kind of the, if the light is incident on the any kind of the media, if there is a reflecting index difference, so the direction of the light will also change. So here you can see, so this is the light, so there is a media, if it's incident, so when it's reflected back, it can propagate to a different direction. Okay, the direction of the light can change. So what will happen in case of the meridional ray and in case of the skew ray? Here you can see, so in case of the meridional ray, what will happen when light is incident on the fiber? So there is a this is called the fiber axis. Okay, this is called the fiber axis. So light should follow the total internal reflection. So there is a reflecting index beta 1 and there is a reflecting index beta 2. So when light incident on the interface of the coherent cladding, when light can create an angle with the fiber axis, then it can propagate through the fiber and it should follow the total internal reflection. So here in this case of the meridional ray, so only there is a the change in the direction when it hits the interface of the eta 1 and eta 2. Okay, so there is a change in the direction of the incident light which follows the total internal reflection. Okay, so when it hits the interface of the eta 1 eta 2, then only the direction of the ray will change. Okay, again if it hits the interface of the coherent cladding, then only direction of the ray will change. So that means it is following the zigzag path. It is following the zigzag path. I think it is clear for you. So there is a no change in the direction through the fiber axis. Through the fiber axis, there is a no. Sorry, it is like that. Okay. So it's when it hits the one interface of the coherent cladding, then the direction will change. Again, when it hits the other face of the other interface of the coherent cladding, then the direction all change. Okay, so before that there is a no change in the direction. So this is called the meridional ray and it follows the zigzag path. So when you see from this side, this face of the fiber, okay, this is the radius diameter of the fiber, core diameter. So you can see light the you can see the light is like the straight line. Okay, it is, you can see it is the straight line. It's going up and going down, going up and going down. So from if you again if you see from this side also, you can see it is going up and going down, going up and going down. So light is like that, the direction of the light is like that, it's up down up down up down. But in case of the skew ray, what will happen with the fiber axis? So what will happen in case of the skew ray? So it will be like that. So before, when it enters into the fiber, okay, before it hits the interface, okay, before it hits the interface, the direction will change. Okay, I can show you. is a fiber axis. Okay, so light enters, the direction is changed. Again it hits the interface, the direction is changed. Okay, again so here you can see, so when it crossed the fiber axis, the direction is again changed. Okay, again like this way. Okay, so here also the direction is changed, it's diverted again. So again it's come here, again the direction is changed. Okay, so after certain period of, after certain distance of time, the direction of the light is changed. It's not only when it interface, when it hits at the interface of the coherent cladding. Before coming to the interface of the coherent cladding, before coming to the interface of the coherent cladding, it hits the it changes the direction of the ray. Okay, it changes the direction of the ray. So when you see from this side, so you can see it is following the rotating path. Okay, so each and every time, after certain period of time, after certain distance, okay, the direction is changing. So here you can see, here this point to this point there is no change in the direction, but here you can see this point to this point there is a change in the direction. Why it is happen? Because in the core the reflecting index is not constant. Okay, the eta 1 is not constant. Eta 1 is not constant. Here also at each moment the direction is changing. Each moment the direction is changing. So it is following the rotating path. So it is following the rotating path. Here you can see, if you see from this side, if you see the face of the core, it will be like that only. Okay, so not straight line. Okay, rotating path, rotating ray. You can see the rotating ray. That's why the name is called the skew ray. I think this skew ray I clear for all of you. So there are some difference between the meridional ray and the skew ray. Okay, meridional ray. So normally it confines the core axis of the fiber. So because here it is not changing, it follows the helical path, right? So these are the, so easy to track. So you can easy to track the this path of the fiber because it is straight line path. So here it is circular path, so you cannot easily track the optical signal, right? So these are the some the difference between the meridional ray and the skew ray. Now come to the mode of the fiber. Okay, now come to the mode of the fiber. So mode of the fiber, this I have already discussed in the last class. What is the mode of the fiber? Normally when any light is incident on the fiber, okay, you can see the direction is changing. Okay, sometimes it like this only, sometimes it is like this only. Okay, so the multiple numbers of the light can incident through the optical fiber, right? So the which way light is following. Okay, so suppose one ray is going like this way, another ray is going like this way. So this decides the different modes. Okay, this decides the different modes. What is the mode? The nature of the propagation of the electromagnetic wave. The light, that is the electromagnetic wave only. The light, that is the electromagnetic wave in a waveguide. So optical fiber, that is also a waveguide. Right? Optical fiber, that is also a waveguide which guides the wave, electromagnetic wave. Okay. So here uh, so number of waves, how many number of waves are propagating through the fiber? Okay, based on the angle, based on the total internal reflection angle, okay, or interference, based on the angle or interference, the mode can achieve, right? So how many lights ray are propagating through the optical fiber which follows the total internal reflection? Based on the total internal reflection and based on the change of the angle, the mode can achieve inside the fiber. Single mode and the multi mode. So when single mode happen, if there is only the single light. Okay, so mode means the nature of the propagation of the electromagnetic wave. That is the number of the wave that allows to propagate, right? So the single mode is only the single light. So you can see the straight line light is passing through the fiber. It follows the total internal reflection, but you can see this is the straight line light. Okay, this is the entire straight line light passing through the optical fiber. Okay, so that's the one mode is that is the multi-mode fiber. So in multi-mode fiber, so multiple rays are propagating through the fiber. In case of the multi-mode fiber, numerical aperture is the important. In case of the single mode fiber, the modal field diameter is important. This I will discuss in the next class. Okay. So the how the light is propagating through the fiber, how many lights are propagating through the fiber, in which direction light is propagating through the fiber, that defines the mode. Okay. So here in this diagram, in these three diagrams, you can see that so in all cases the code reflective index is greater than the clear reflective index. This is the so one incident light is following through like this way. Okay. So whatever the electromagnetic wave, this electromagnetic wave, it has the electric field and the magnetic field. Okay. So normally when you want to distribute, when you want to express any kind of the electromagnetic wave, normally we used to prefer to tell the electric field distribution. Okay, here you can see these are the electric field distribution. How the light is propagating through the fiber, that can change the distribution of the electric. Normally, suppose you can see this electric field can write as a suppose E is equal to E naught cos omega t plus phi. Okay, this is the electric field distribution. Normally, the electric fields, this electric field that is in the function of the distance ER. Okay, the through the distance the distributions can change. This is called the electric field distribution. Okay, so here you can see light is propagating like this way. Now, now here the light is incident like this way. Now you can see in this case that angle, you can see this angle and this angle is different. This angle is larger than this angle. Okay, so if the incident at the interface such a way that the angle is more than this one, you can see when it reflected back from interface and it's going to the other interface of the coherent cladding, there could be some distribution, some signals are penetrating into the fiber. Okay, penetrating into the fiber, that this will give the such kind of the distribution. So if it is like that, so then the one distribution only the single peak of the electric field. So if it is like that, you can see this is the double on the positive side and the negative side, two different distributions are there. Okay, next here you can see this angle is again more than this angle. Now you can see when it hits the interface, it's tried to penetrate the into the cladding. It's tried to penetrate into the cladding. Okay, so then you can see the this radius. This is called the field distribution radius. This is 6 pi. Here it is 2 pi. Here it is 4 pi. Here it is 6 pi. Okay. So here also it's penetrating into the core. So then there will be the three distribution. Okay. So one is this one. Here you can see here it will be like that one. Okay. Two positive, one negative. One is the one positive, and the one positive, one negative, and is the positive, negative again positive will come. Okay, so how the light is incident on the fiber, what I told, what is the mode. So these are the different mode. So this also depends on the frequency or wavelength of the signal. Okay, frequency of the wavelength. So there are the various of optical wavelength the signal can enter into the fiber. Okay, so there is another term is called the cutoff frequency. Cutoff frequency. Okay, so optical fiber, these are designed based on some frequency. Okay, the optical fiber, these are designed based on some frequency. Suppose this is designed for as one frequency, suppose or lambda frequency fc. Okay, so these are the different frequency light is incident on the fiber, right? Okay, so light should be incident like such a way that it can give at least one mode, at least this kind of the distribution it can give. Okay, so if suppose the if frequency is greater than these frequencies are greater than this frequency, then the different modes it can achieve. But suppose one frequency light is incident through the fiber which frequency is the less than the frequency of the optical fiber, then it can only give the single mode or the some single mode, or it can will not give any kind of the modes. Okay, when you cut to the modes means no modes are propagating. All the signals are attenuated inside the fiber only. Attenuated means the light is incident like this way. So it is not reflected back. It is going into the core only. So here it follows the total. For all the cases follows the total internal reflection. But some signals are penetrate into the core. Okay. These are distributions only. Okay, but the some signals are at least one mode should be propagate, or at least one signal should be propagate, right? So this depends on the cutoff frequency or the that which frequency the optical fiber is designed. Normally in this optical fiber is the waveguide, it follows the one what waveguide rule. So the cutoff frequency is the frequency at what the optical fiber is designed. So if the different kinds of the optical signals and different which is having the different frequency that can propagating through the fiber, so those frequencies should be greater than that cutoff frequency for achieving different modes, or it should be equal to cutoff frequency for achieving at least single mode, right? So these I'll also discuss in the next slide. So here you can see the TE0 is the minimum mode. This is giving the single mode. This is giving the single mode. So there you can calculate a particular one frequency. Okay, one frequency for this mode, right? So this frequency should be equal to FC, the cutoff frequency where the optical fiber is designed. Okay, so such frequency wavelength because the how the light is incident the this way the distribution is changing. If some frequency say optical signal has the some frequency which are greater than fc, then it will give those modes. If some frequency is less than fc, it will not give any mode. Okay, it will not give any mode, right? So because the why the light is incident in different angles through the fiber, because there are the high frequency signal as well as the low frequency signal. Based on the frequency of the wavelength signal, the light is incident angle of the light is changed when it hits the interface of the core and plating, right? So this is the issue. So if different frequency signal, optical signal can the different distribution, which is named as the transverse electromagnetic. Transverse electromagnetic TE is the transverse electric field. So normally the electric field is moving like this way. Normally its amplitude is oscillating suppose in y-axis, and it is propagating through the z-axis. Transverse electric means so in case of the electric field, it has suppose Ex plus Ey plus Ez. Okay, Ex plus Ey plus Ez. So in Ez will be 0. There z direction there will be no component of the electric field. So that is the transverse electric field. Okay, so this is the different electric field and magnetic field orientation name. Okay, TE1. So here it is the only one distribution TE0. Here it is two distribution TE1. Here it is three distribution TE2, like that, this way. I think this diagram is clear. So these distributions are getting based on the different wavelength of the optical signal is propagating through the fiber. Okay. So the frequency I told, so in case of the optical fiber, the corresponding frequency that is defined as a V number. Okay, the normalizer, the corresponding frequency that is defined as a V number. So normally the corresponding frequency below which the mode cannot propagate. So that's I told the the frequency, some frequency signal is propagating through the fiber, incident into the fiber, which wavelength is less than the FC, then it will not propagate. The corresponding signal, the corresponding propagation mode will not propagate. It can attenuate. This FC, this is called the corresponding normalized frequency or cutoff frequency, or it is also known as the B number. Okay, it is also known as the B number. For particular mode to propagate inside the fiber, B number of the fiber must be greater than B number of the corresponding frequency of the mode. Okay. So what are the incident frequencies are there? Those frequencies should be greater than FC. Okay, so for FC is for achieving the one particular mode. Okay, for achieving the one particular mode, right? So the frequency of the optical fiber that should be greater than the FC or some particular mode, right? So suppose for TE01 mode there will be a corresponding FC. This FC should be greater less than this F, the optical fiber, right? So whatever F's are there less than FC, then this will not propagate, or signal cannot propagate to the fiber, right? So the normalized frequency that is defined as a D number. So whatever the cutoff frequency I told, that is the defined as a D number. D number is equal to 2 pi a lambda root under n1 square minus n2 square is equal to 2 pi a lambda into n. So this is that we know the n is equal to root under n1 square minus n2 square. So the a is the radius of the core, and 2m is will be diameter of the core. Okay, lambda is the optical frequency wavelength, at which wavelength the optical light is incident on the fiber, right? So this is the B number, right? If B number is greater than so there is a called the mode that all there. So this is the B number. So whatever cutoff frequency I told, the so each fiber is designed for a particular frequency. So there that frequency should be the corresponding cutoff frequency. So for achieving this electric field distribution, one peak. So for achieving one peak, there will be one frequency. So if the light is incident in such a way that which can achieve this frequency, this distribution, right? So this is the FC, right? An optical fiber should follow some modes but for case of the single mode, the optical fiber frequency is equal to that the single mode frequency TE0, the one mode frequency is fine. But for the multi-mode, the optical fiber frequency should be greater than the different modes are there. Now, for different modes, different frequencies are getting. Those frequency, the optical fiber frequency should be greater than those frequency, right? So this is the B number. So if you have the optical frequency signal, okay, and you know the coherent cladding diameter, so you can calculate the how many modes should be propagated through this optical fiber. Okay, I'm showing you the help of the one numerical. So this is the B number formula and the number of modes. Okay, number of modes equal to B number square by 2, that is for step index and the gradient index. So that I told the skew ray and the meridional ray, right? In case of the meridional ray, I told that the core reflecting index is constant. But in case of the skew ray, the core reflecting index are different, right? So for that, this if the core reflecting index different, so the fiber is named as the cladet. If the constant reflecting index inside the core, the fiber is named as the step index fiber. This I will discuss in the next lecture again. So number of modes normally n is equal to b square by 2 for step index. Either it is single mode or multi mode. So for step index fiber, the n is equal to number of modes is equal to b square by 2. For multi mode fiber, the n is equal to b square by 4 for gradient index multi mode or single mode fiber. So both are maybe single mode or multi mode. Here it is also single mode or multi mode. Okay, so if you getting the B number is 2.402, okay, that means only the single mode. Okay, so here if you put the B 2.404, whatever n is equal to get, it does not tell anything. Okay, so whatever n is equal to, you get this n is If V number you are getting the less than 2.4, it's not required to calculate the number of modes. Simply it will be the single mode fiber. If V number is greater than 2.4, you will get from this equation. Okay, then you have to calculate the number of modes either using this formula or using this formula based on the types of the fiber. Then you can calculate get the how many modes are propagating through the fiber, right? So this is the cutoff condition. Okay, this is the cutoff condition. B is equal to 2.405, right? Now, so again I am telling the cutoff condition, so this is little bit confusing. So whatever optic, so okay, I first I show you the program array numericals, then I'll conclusion. I'll tell the conclusion of the this thing, the dominant mode or the cutoff frequency and the frequency of the optical fiber. So here there is a core diameter is the 6 micrometer. Okay, core reflecting index eta 1 is equal to 1.45. Critical angle. Critical angle phi c is equal to 87 degree. You have to calculate the reflective index of the cladding. So what is the, if you put the Snell's law at the core cladding interface, if you remember the my last lecture, so eta 1 sine phi c is equal to eta 2 sine 90. You are putting the critical condition at the interface of the core and cladding. So if you put the eta 1 formula sine, so 1.45 sine 87 degree is equal to eta 2. So from here you will get the eta 2 1.48. Okay, you will get the eta 2 1.48. You can check the calculation, right? Now acceptance angle of the fiber. Okay, so acceptance angle is equal to sine inverse. Theta naught is equal to sine inverse the Na. Okay, so Na means sine inverse root under eta 1 square minus eta 2 square. So if you put eta 2 formula here and eta 1 formula here, you can get the value of the theta naught is equal to 4.366. Okay, just check. It is 4.8, 1.448. Okay, this is 4.366 you get, right? Last one is the number of fiber modes propagating through the fiber where wavelength of the light is 1 micrometer. Okay, so what I told that. So when such optical such wavelength of the light, so if the such light wavelength is right, the some various wavelength light can propagate through the fiber, but if the optical fiber is designed such a way that it has one frequency. Okay, so that frequency, so whatever optical fiber is designed, that frequency should be greater than, so the frequency of the light is propagating through the fiber, right? So the various frequency of the light can propagate through the fiber. So those frequency should follow the V number. The V number should be, V number of the fiber should be greater than the corresponding frequency of the wavelength or the optical frequency, optical signal. Okay, so here you can see, so suppose the optical fiber is designed for a some frequency, but I will check whether the optical signal which has the 1 micrometer, it can give any mode or not, right? So to check how many modes it can give, right? So that you can use for the same fiber, you can use for the single mode or as well as the multi mode. So from that I can understand whether this fiber will be used for the single mode or multi mode, right? So the V number is that, sorry, 2 pi a lambda, okay, root under n1 square by n2 square. Okay, the 2 is here, the diameter is given 6 micrometer. So that means pi into 6 into 10 to the power the lamb 6, only you can write the 6. Okay, because the wavelength, my unit, the micrometer, and the this one, the diameter is the same unit. Okay, So here wavelength is the 1. Okay, and this value you know, suppose this is the eta 1 square by eta 2 square. So from here you can calculate the V number, it will be 1.435. Okay, not required to convert the unit. Okay, it is also 6 micrometer, it is also 1 micrometer. Instead of 2a, I have written the 6 because the diameter is given, the pi is mentioned, and the 1 is equal to 8 ounce. So here we will get. So if this V number is the 2.45. Okay, so this is the cutoff frequency, you can see. The cutoff frequency you can see. So that this the V number of the particular wavelength light. Okay, that is less than 2.45. That means only if the 1 micrometer wavelength light is propagating through the fiber, it can only produce the single mode. Only it can produce the single mode. Okay. Yeah. So if different wavelength length is, so if the lambda is different, you will get the different V number. If lambda is different, you can get the different V number, right? So the 2.54 is the boundary to set the how many modes are propagating through the fiber, right? So again, I am telling the number of the modes is the how the optical signals are incident on the fiber, that gives the idea of the mode, right? So not all the optical signals can produce the various modes. It also depends on the wavelength of the optical signal, the way the light is incident on the fiber, the angle. So everything it depends. Okay. So normally, so we will have the one cutoff wavelength. Okay, one cutoff wavelength or one cutoff frequency. Okay. So the optical fiber will be designed for a particular frequency. Okay, which and allow the multiple frequency of the optical signal, and those frequency of the optical signal should have some modes. At least it should have the single mode, right? So how can you calculate the mode? So there is a formula. This is the 2 pi a lambda by root under n1 square n2 square. The lambda is the optical signal wavelength. So normally the lambda is equal to 2.45. That value, okay, that value is considered for setting the t is 0. T is 0 is the single mode for achieving the single wave. By considering the t is 0, the v number is the frequency only. The v number is the frequency. V number is calculated as a 2.45. Okay, minimum cutoff frequency, right? So based on the V number, so the whatever optical signal light is propagated through the fiber, either it is whether it is achieving the single mode or multi mode, you can calculate, right? Okay, now come to the various types of the optical fiber. based on the Based on the reflecting index that I told, if the constant reflecting index, then step index fiber; in multiple reflecting index, then the gradient index fiber. Okay, and the mode I told, only the single ray is propagating through the fiber, that is the step mode, single mode. If the multiple modes are propagating through the fiber, then it is the multi mode, right? Multi mode fiber. So these are normally used for the long distance communication. These are used for the short distance communication. Why that I tell now. Okay, or next class I will tell. So based on the step index and gradient index. So in case of the single mode also, there you can design the step index, gradient index fiber. In case of the multi mode also, you can design the multi mode step index and gradient index fiber. So different fibers have some advantages and the disadvantages, right? So for single mode fiber, that I told, the it follows the only the straight line and only the fundamental mode or the only the lowest order mode, which is belongs to the cutoff frequency. If F is equal to Fc, okay, then only the single mode fiber. You can only propagate the single mode. Okay, the F is the optical signal of the F is the frequency of the corresponding optical signal which is entering into the fiber. Fc is the cutoff frequency for achieving the only single mode, the T is 0 mode, for achieving the T is 0 mode, right? Okay. Uh, so normally the laser source is used. So laser source, it can confine into the only single point. Laser source is not using the lens. It can easily, the lasers, whatever lights are emitting from the laser source, it can confine into the same point. If the light is confined into the at the only the single point, it can produce, give the single mode. Why you need the single mode? Because the only the same light is propagated. Whatever information is there at one end of the fiber, we try to get the same information at the other end of fiber. So there is a no loss of the signal. But in case of the multimode, different ray are reaching at different point at the other edge of the fiber, okay, which can produce, which can, we cannot get the entire information at other end of the fiber, okay. Different points, different rays are transferring at the other end at different points, so that we cannot get the entire information. Okay, so here I can get the data, whatever data I am entering in that point, you can get the same data, because there is a no pulse broadening, no interference of the multiple signal. If there is interference of the multiple signal, the data will be lost. Okay, so there is no other signal, only the single signal. Whatever information are passing through this signal, entire information will be passed at the other side of the signal. So using the laser source, we can launch the single mode light. Okay, we can launch the single mode line through the fiber using the laser source, because it can confine the light at a particular point for the laser source. Okay, so these are the some advantages and disadvantages. So advantage, less dispersion, the degradation means, the suppose this the information, so whatever same information, the amplitude, same amplitude at the source, at the one end of the fiber, the same information will get, the same amplitude will get the other end of the fiber. The dispersion means, what it is. So suppose the information is like the shape of the pulse is like that only. In case of other end of the fiber also, shape of the pulse will be like that. The degradation means the shape of the pulse will change if there is any interference with the other signal. So in case of the single mode, the less dispersion, less degradation, and we can, if there is a no degradation, whatever information we are passing, we can get the launch of lots of data through the this single mode fiber. And the drawbacks are that, the core diameter is very small in case of the single mode fiber, so it is very difficult to design. And the launching of the light, only the single ray of the light should propagate through the fiber, so launching of the light is difficult, as well as the it is expensive and difficult to fabricate. So these are the some advantages and disadvantages. Main advantages are lots of data can propagate through the fiber, and entire information we can get at the other side of the fiber, and the less degradation, less dispersion. So related to single mode fiber, there is a one important term which is called as the mode field diameter and the fiber bit length. These two terms are important. So this I'll discuss in the next class, and followed by the some multi-mode step into getting this fiber advantages and disadvantages. So thank you. Please like, share, and subscribe my channel.